Hello and welcome to my channel. EKS Blueprints let you quickly, with little knowledge of AWS, create fully bootstrapped and production-ready Kubernetes clusters. I'm not entirely convinced if it's a good thing. As with any other shortcuts, in the long run, especially if you need to maintain EKS clusters for over a year, using these modules can become a nightmare. There are so many abstractions and dependencies. For example, the main Terraform module is a wrapper around another Terraform AWS EKS module, and so forth. Blueprints also have a Kubernetes add-ons module that allows you to install managed add-ons such as EBS Driver and self-managed add-ons such as EFS, AWS Load Balancer Controller, Cert-manager, and many others. All of those self-managed add-ons simply wrappers around Helm charts. Anyway, in this video, I'll show you how to create VPC from scratch using Terraform. Then we'll use EKS Blueprints to provision EKS cluster. And we'll install a few managed and self-managed add-ons such as EBS and EFS CSI Drivers, AWS Load Balancer Controller, Metric Server, Cert-manager, Cluster Autoscaler, and Karpenter. Also, I'll show you how to add IAM users and IAM roles to AWS EKS cluster. And finally, we'll create a Fargate profiles and deploy a few sample apps. First of all, we need to create VPC. I'll show you how to use plain Terraform resources as well as Terraform VPC module. In my opinion, you should use modules only when you understand the basics. AWS provider is needed to authenticate with AWS and contains a set of resources that you can use to interact with the cloud in declarative way. Then we have a VPC with a CIDR block. Many third-party tools would also require DNS support, so I would suggest that you enable it from the beginning. Internet gateway to provide internet access for public subnets. Then we have two private and two public subnets. Public subnets will use internet gateway as a default route, and private subnets will use a NAT gateway. Now, the important part is subnet tags. For EKS to function properly, you need to have Kubernetes cluster tag with your EKS name. The value can be owned or shared. This tag, for example, will be used by Karpenter to discover and autoscale your cluster. If you want to expose your applications to the outside world, you would also need to assign internal ELB tag to private subnets, where you want to create private load balancers, and just ELB tag for public load balancers. Then we have a NAT gateway. I would suggest that you manually allocate public IP addresses in case you need to whitelist them with your clients in the future. Even better is to allocate multiple IP addresses ahead of time in case you would need to perform any migrations. And we have public and private routes that assign to all our subnets. Now, if it's clear to you, instead of creating all those Terraform resources, instead you can implement the same functionality using a single Terraform module. Always pin your modules to a specific version. You can Google this module and find all input and output parameters. Let's call this VPC main module. Then we'll use the same CIDR as with plain Terraform. Specify availability zones and provide CIDR blocks for private and public subnets. Also enable DNS support. There are multiple combinations that you can use to deploy the NAT gateways. I always created a single NAT and never had any issues with it. Then we need to create similar subnet tags. If you decide to use a different name for EKS, replace the demo here. Now we're ready to use EKS Blueprints to create EKS cluster. Another way to pin Terraform module to a specific version is to use git tags. Give it a name, demo in my case. Let's use the latest EKS version 1.25. Some applications may require access to AWS API. The best way to grant access is to use IAM roles for service accounts. For example, AWS Load Balancer Controller would need access to AWS API to create load balancers. It's enabled by default. I just want you to be aware that you have it out of the box. Now, in case you use plain Terraform resources, you would use AWS VPC main.id. I'll be using Terraform VPC references instead. Same with private subnets. You can use plain resources or a module. Then we'll create a single managed node group for the cluster. Give it a name general and set appropriate autoscaling configurations. Keep it in mind, to autoscale your EKS cluster, you must additionally deploy either cluster autoscaler or a Karpenter. Since this module tries to modify AWS auth config map, we need to declare Kubernetes provider. We can use references from the module. Also, make sure that you have AWS CLI installed on the machine where you run Terraform. There is another way to use tokens without CLI. That's all. Let's go ahead to terminal and apply Terraform. First, you need to initialize and run apply. It may take up to 10 to 15 minutes to create a cluster. To connect to Kubernetes, first you need to update your local Kubernetes config with the AWS EKS command. Then you can run something like kubectl get nodes to verify that you can connect to the cluster. Next, we'll install EBS CSI Driver using managed EKS add-ons. We need this driver to be able to attach EBS volumes in case you want to run stateful applications on Kubernetes. It can be your own stateful app, some messaging systems such as Kafka, or perhaps a database. Why not? To deploy EBS driver, we'll use another Terraform module provided by EKS Blueprints. It's called Kubernetes add-ons. It's a combination of managed and self-managed add-ons that you can enable in your EKS cluster. First of all, we need to link this module with the EKS cluster. Some of the EKS add-ons enabled by default, such as CNI and Core DNS, but since most of the people still run only stateless applications in the EKS cluster, EBS driver is disabled by default. To enable it with this module, simply flip it from false to true. Since it's a new module, we need to initialize Terraform and apply it. Even before you enable this add-on, EKS creates a default GP2 storage class, but without this EBS driver, all the persistent volumes will be stuck in the pending state, since they need a provisioner to allocate EBS volumes and attach them to the nodes. Now, in this simple example, we'll create a stateful set which is based on Nginx, just to validate that we can attach volumes to the pods. Stateful set has a template block that allows you to dynamically create persistent volumes for each new replica. So if you set replicas to 5, Kubernetes will create 5 persistent volumes and attach them to your pods. In the following example, I'll show you how to share the same volume between multiple pods. Let's go ahead and apply this YAML file. In a few seconds, you should be able to get a new PVC with a bound state. Then you can run kubectl get pods in the default namespace to ensure that the volume is attached to the pod and it's running. If you don't enable this EBS driver, a pod will be stuck in creating state. Next, we'll install EFS driver. First of all, it allows you to share the same volume between multiple pods. It supports read-write many mode. Second, it's elastic and can grow in size dynamically, and it is highly available storage system, but slightly more expensive than EBS. To install it, we'll use self-managed EKS add-ons that use Helm charts. To install EFS driver, we can use the same Kubernetes add-ons module. Compared to the previous EBS driver, provisioning of EFS is implemented as a Helm chart. When you enable this driver, this module will use Helm provider with the Helm released Terraform resource. Since it's a Helm chart, optionally, you can provide some Helm settings. For example, specify the repository. Out of the box, this driver will use 3.2 version, but by using the config, we can upgrade the Helm chart to the latest version. You can modify the namespace if you wish, but I would suggest leaving it as is. It's also possible to override some charts values, but the whole point of this EKS Blueprints module is to provide default settings that you would use. If you decide to override Helm values, just don't use this module and install Helm charts directly using Helm provider. We also need to initialize the Helm provider to be able to authenticate with EKS and install Helm charts. It's a similar config that we used in the previous provider. Also, it's important to understand that it's not enough to configure EFS in your cluster. I think it's a little bit misleading for beginners. Enabling this add-on is just halfway to getting there. You also need to create EFS file system in AWS. Let's create a new file. This Terraform resource will create EFS in AWS. You can also Google this name to get a full set of supported parameters. Now, if you would use plain Terraform resources to create VPC, you would need to define two separate mount targets for each availability zone that you use. The first one is for US East 1A and the second one for US East 1B. Since I use Terraform module to create VPC, it exposes private subnets tuple that I can use for each block to dynamically create mount targets in all availability zones. You need to link those targets to EFS file system. And also important, when you create EKS cluster, you get a primary security group that you need to use here to grant network access to those targets. Otherwise, you won't be able to allocate volumes from EFS. The next step is to create a dynamic Kubernetes storage class. Dynamic means that you don't have to create persistent volumes manually. Instead, you just need to create persistent volume claims or use a stateful set template block. In this storage class, you also need to have a link to AWS file system. Let's explicitly depend on the add-ons module before we attempt to apply this class. That's all configuration needed to set up EFS in your EKS cluster. Let's go ahead and apply Terraform. You can ignore this warning since it's a part of the module implementation. If you run kubectl get storage class now, you'll get a new EFS class with our provisioner, which we deployed as a Kubernetes add-on. To test, let's create a persistent volume using our EFS storage class. While using EFS, we can specify read-write many access mode that allows attaching the same volume to multiple pods. Also, EFS can dynamically grow in size, but since this PVC requires storage property, we must put something there, but it's going to be ignored anyway. Next, create a pod and use that persistent volume claim. And the same thing for the second pod, we use the same PVC in both cases. Now, if you would use default GP2 storage class, the volume will be attached only to a single pod and you get an error message from the second one that the volume is already in use. Let's get PVC first. And if you get pods, you'll find that both pods are running, which means that our volume is successfully attached to both pods. Next, we'll install AWS Load Balancer controller using self-managed EKS add-on. It replaces in-tree controller to create network and application load balancers. Also, you can use it to create ingresses for your applications and expose them to the outside world. By default, this controller creates application load balancer for each ingress, but there is a way also to share the same load balancer between multiple ingresses. Also, it supports two modes: instance mode. In this case, your service must use node port, and IP mode. IP mode is better, since it removes additional network hop from the route. To install AWS Load Balancer controller, we also use a self-managed EKS add-ons module. Controller itself is not used to proxy any traffic compared to Nginx ingress controller, so in this instance we'll keep all default settings. Let's go ahead and apply Terraform. By default, it will create ALB ingress class. Now, to validate, let's create a simple deployment object based on Echo server. To use IP mode, we need to create a service of type cluster IP. On the ingress resource, we need to switch instance to IP mode using target type annotation. Also, we can either create public ingress that can be accessed from the internet or a private one to expose applications within VPC. Then specify ingress class and optionally provide a host. Switch to the terminal and apply YAML files. Make sure that the pod is running and check ingress resource. If you get external address, means that the load balancer was successfully provisioned. Let's wait a few minutes and verify that we can resolve DNS name locally. Now, to quickly check the ingress, we don't need to create a CNAME record. We can simply use curl and host header. Instead of IP address, use a load balancer hostname. It appears that we can access Echo server deployed in Kubernetes cluster from our local machine. Next, we'll install metric server and Cert-manager, and I'll show you how to enable cluster Autoscaler. As with previous add-ons, we'll use the same Terraform module. First, let's enable metrics server. Usually it's used with a horizontal pod autoscaler, but you can also use it to quickly get CPU and memory usage of the pods and nodes with kubectl top command. Second is a Cert-manager. The most common use case for Cert-manager is to dynamically obtain and renew TLS certificates from Let's Encrypt when you expose your applications to the internet using Ingress. It can also be used to issue local certificates, for example, to enable mutual TLS for Linkerd service mesh. And finally, cluster autoscaler. It's much easier to enable cluster autoscaler than the Karpenter. If you need a quick way to automatically scale your cluster, use this first. When you get enough experience, you can shift to Karpenter. I'll keep it disabled since later in the tutorial we'll install Karpenter and you cannot combine both of them in a single cluster. That's all, go ahead and apply Terraform. To verify that metrics server is installed, run kubectl top pods to get CPU and memory usage. Let's also verify that the Cert-manager is up and running in the cluster. Next, we'll deploy Karpenter, which is a project that helps dynamically autoscale your cluster. Cluster autoscaler works by adjusting the desired size on the autoscaling group. Karpenter, on the other hand, analyzes your workloads and creates EC2 instances directly, based on the need. It can help you to save money and is also great with batch workloads such as Airflow, since it reduces latency and can spin up new nodes more quickly. Let's go back to the add-ons module and enable Karpenter. Also, let's update the Karpenter Helm chart to the latest version. This is the first part. In the next part, we need to create instance profile and define provisioner. To automate deployment, let's also use kubectl Terraform provider. It's a very similar setup as with Helm provider. But in this case, we must specify the source of the provider, since it's not managed by HashiCorp. Next, create a native node termination handler and IAM instance profile by using Karpenter Terraform module. Now, we also need to specify what type of instances we want to create with Karpenter, including family types and sizes. The final object that we need to create is AWS node template. We need to specify the private subnets where we want to create those EC2 instances and EKS security group by using tags. Also, we need to attach a new instance profile to each EC2 instance created by Karpenter. Since it's a different profile that was created by EKS node group, we need to explicitly add that profile to EKS auth config map to allow that EC2 instances join the cluster. That's all, switch to the terminal and apply Terraform. To verify that Karpenter can create new EKS nodes, create a deployment object with 5 replicas. I would also suggest that you check Karpenter logs for the first time when you're trying to scale the cluster. You may get some warnings, but you can ignore them. Let's apply our deployment. In a few seconds, you should see that new nodes are joining the cluster and Kubernetes schedule all pending pods. Next, if you want to fully automate your cluster and use serverless EKS, you can create Fargate profiles. You can combine Fargate with regular node groups. You just need to specify the Kubernetes namespace and optionally labels to target workloads. Go back to the blueprints Terraform file. It's actually very easy to create a Fargate profile. Give it a name, for example, staging. Provide subnets for the nodes and specify the namespace in Kubernetes cluster. In this instance, all pods created in the staging namespace will use Fargate serverless nodes. Basically, EKS will create a dedicated node for each pod you spin up. Let's apply the Terraform. To test, create a new staging namespace and a deployment with a few replicas. Let's go ahead and apply it as well. Now you can see 3 pending pods. In a few seconds, EKS will create 3 new nodes with Fargate prefix and schedule all the pending pods. In some instances it's cheaper, in others more expensive. So if you decide to use Fargate, you need to test it on your own workload. Finally, I'll show you how to add additional users to EKS cluster. You can either add IAM users directly to the cluster, but in this case you must update Kubernetes config map every time you onboard a new user. Since EKS does not support IAM groups, The better approach is to create IAM role and add it to the EKS. Then you simply allow certain users to assume that role. Let's create a new Terraform file and define IAM policy that allows users in your AWS account to assume a role with access to EKS. You can also grant access to your EKS cluster from other AWS accounts. Next, create IAM role that you allow your developers to use in order to access EKS cluster. That role will get read-only access within the Kubernetes cluster. The next step is to define IAM policy with EKS access to view workloads in AWS console. Attach EKS console access policy to developer IAM role. The second part is to create cluster role within Kubernetes cluster with get, list, and watch access to Kubernetes objects. Then bind this role to the new reader Kubernetes group. Then apply the Terraform code. Now let's create a test IAM user in AWS account that will get read-only access. Create a new user and attach a policy to assume developer role. Also, we need to generate new credentials to create a local AWS profile. Download credentials file. Before we attempt to use a new user, you can check if your current user has admin access to Kubernetes by running kubectl auth can and 2 stars. If the answer is yes, it means you have admin access to cluster. Now let's create a new AWS profile with new credentials from the user. Use AWS STS to check if the credentials are valid. Next, create another profile, but in this case, use a text editor. Let's call it developer and use your new IAM developer role. As a source, specify the user that has permission to assume that role. In my case, it's Anton IAM user that we just created. Also, verify that you can assume that role by using developer profile. To add a new entity to EKS, we need to update auth config map. Use the ARN of the developer IAM role and bind it with airbag Kubernetes reader group. Apply the Terraform. Update Kubernetes context with developer provider. If you try to run can auth command, you'll get no, meaning you don't have admin access anymore. Let's check if we can create pods. The expected answer is no, but if you try to get a pod, the answer is yes, since the reader airbag group has read access to pods. To support my channel, I offer mentorship and consulting services, details in description. That's all for this tutorial. Thank you for watching and I'll see you in the next video.